All right, last time we looked at an example of what we call brute force analysis. And what we saw was that brute force analysis works, but it's not very efficient. It generates a lot of variables, generates a lot of equations, and some of those equations are dependent on top of that. So the question is how can we make the process of analysis simpler? Well, let's look at that today. Let's look at some analysis shortcuts. And in looking at these shortcuts, we're going to introduce a couple of new definitions. The definition of series and the definition of parallel. Now, those are words you have undoubtedly heard all your life, but in this case, there is a specific definition we're going to use which applies to circuit analysis. So, let's first look at a particular example of what's called a single loop circuit. And this is exactly what it sounds like. It is a circuit which contains only a single loop. Now in this respect, this looks very much like the example of the defibrillator we did before. Let's add some component values to it. So I've got two voltage sources, 10 volts, 5 volts. Notice the polarity of the 5-volt source, negative to positive. This, of course, is positive to negative. And I've got three resistors, R1, R2, and R3. So only one loop, only one path around this circuit. Now, we could go through and do this brute force. But before we jump into that, let's consider something that we call a series connection. In this circuit, every element is in series with the two elements it is connected to. So what does series mean? What does that mean for analysis? By definition, two elements are in series when they are connected by a single node with no other elements connected to that node. So let me draw a couple of diagrams, a couple of examples here. I've got two elements, A and B. And they are connected together by a node, and there's nothing else connected to that node. Those two elements are in series. Now, by contrast, what if I drew this? If I had three components or three elements connected together, D and E are certainly connected together at that node, but there is a third element that is connected to it as well. So none of these elements are in series with each other. So Series means there is one connection, a single path between those two elements. So what are the implications for that? Well, let's define a couple of currents. Call this IA, call this IB. KCL holds at that node. And KCL tells me that IA is equal to IB. What goes in must come out. The conclusion is that when elements are in series, they must have the same current. So by inspection, I know this to be true. I don't need to write a KCL equation at that node. There's only one possible path for current to flow. So in this case, I can look at this single loop circuit, and I can say all these elements are in series. I don't need to define a separate current variable for each one of these. In fact, what I can do is I can define a single current. Let's do that. There is one current that's going to flow around that loop. It's got to be the same current in every element. So why in the world would I want to define those as separate variables? There's really only one variable I need to worry about. I'm going to call that I sub s. So now let's go through and let's solve for this circuit. If I've got IS flowing around, I've chosen a clockwise direction, each of the resistors will have a voltage drop. Using the passive sign convention, V1, V2, and V3 must be across those three resistors. The voltages for the voltage sources, of course, are already defined, so I don't need any variables for those. And now I can go through and I can write the equations for this. So let's do the Ohm's law equation. So for Ohm's law, I've got three resistors. Therefore, V1 is equal to 70 times IS, V2 is equal to 30 times IS, and V3 is equal to 50 times IS. So there are my Ohm's law equations. What about KCL? Well, I could write a KCL equation, but it's trivial. For each node, IS is equal to IS. The current going in is the current going out. So that's trivial. You don't even really need KCL because you've already got that single current defined. And so really all you need now is the KVL equation. So KVL, I'll start here in the lower right-hand corner, pardon me, left-hand corner. I'll follow I sub s, follow the direction clockwise. So in this case, 10 is equal to V1 plus V2, those are drops. Then negative to positive, that's a rise, plus 5. And then continue around the loop, I've got another drop, that's plus V3. So 10 plus 5 is equal to V1 plus V2 plus V3. I can substitute, and what I will get is that 15 is equal to 70 times IS plus 30 times IS plus 50 times IS. Solve this, and what I get is that IS is equal to 0.1 amps. Now I want to point something out here. Here's Ohm's law, here's KVL. What is that equation I just wrote? This equation I got by combining the Ohm's law plus the KVL equations, which means this is KVL plus Ohm's law. all together in a single equation. Now, why did I point this out? Because if I wanted to solve for I sub s, I really didn't need V1, V2, and V3. I could have done it this way. I could have simply drawn in the voltage drops across the resistors, not even bothered to define voltage variables for them, and then simply written the KVL equation, just writing the voltages as the resistance times the current. So in this case, just from here, I could have just written this right off the bat. I could have said 10 is equal to 70 IS plus 30 IS plus 50 IS for the drops, and then add 5 for the additional rise, and there'd be my answer. I point this out because this is a shortcut that you're going to find really handy, very useful. In general, when you're doing circuit analysis, it doesn't make much sense to define variables you don't need, variables you don't have to solve for. So if you can eliminate variables by combining equations together, that makes a lot more sense. So there's nothing wrong with writing these and these separately. But if you can just right off the bat start learning to combine the KVL and the Ohm's law equations together right at the start, you're going to find that the problems are a lot easier and a lot quicker to solve. Because this way, I just get one equation. That's all I care about. All right, so this is my example of the single loop circuit. Now let's look at another simple example. In this case, we're going to look at another simple example, a single node pair circuit. And in this case, I'm going to have a circuit which all the elements are connected to the same two nodes. All right, so in this case, I've got two nodes. I'm going to call this node A, call this node B. Keeping in mind, A is this entire thing at the top. That's the node. B is this entire set of wires at the bottom. So the whole thing is node, not just that dot. Okay? Now, the reason why I drew this is because this illustrates another definition. In this circuit, all of the elements are in parallel with each other. So what does parallel mean? Well, just like series, parallel has a specific definition in circuit analysis. Two elements are in parallel when they are connected to the same two nodes at both ends. So again, let's draw a simple example to illustrate what this means, what parallel means. So let's say I've got two elements connected like so. In this case, A and B are in parallel. They're both connected to this node at the top. They're both connected to that node at the bottom. So by definition, they're in parallel. What if I have this on the other hand? So here I've got elements D, C, and D. Are these in parallel? Well, some people will look at it and say, well, yeah, Dr. Holman, they're in parallel. They're side by side. No, that doesn't mean parallel. Parallel means not just orientation, but they are connected to the same two nodes. Is E connected to the same two nodes as D? No. On one side it is, not the other. What about C? No. In fact, none of these are in parallel. But note, D and C are in series, but they're definitely not in parallel. So now, why does parallel matter to us? Well, just as we did before, let's go through and let's define a couple of voltages, VA and VB. This is a simple loop between those two elements. Let's write a KVL equation going around that loop. So in this case, I'll start at the bottom, I'll go clockwise, and what we see is the rise of VA is equal to the drop. And what do you know? By inspection, elements in parallel have the same voltage across them. And so now, given this information, let's apply that to this single node pair circuit. So in this case, I'm going to define a voltage Vs between nodes A and B. All of these elements are in parallel. So the Vs across this 50 ohms is also the same Vs across the 1 amp source. It's also the same Vs across the 40 ohm. It's the same Vs across the 5 amp source. It's all the same. So now let's go through and let's apply KCL and Ohm's law. All right, so I've got Vs across all the elements. I'm going to define a current I1 and a current I2 flowing through those two resistors. Once again, applying the passive sign convention in order to make Ohm's law work for those resistors. I don't need to define any currents for the current sources. Of course, that's already given, already defined. So in this case, I can now go and write my equations. Ohm's law. In this case, Ohm's law says that Vs is equal to 50 times I1. Vs is equal to 40 times I2. KCL, what does that tell us? Well, for KCL, let's look at the top node. So for the A node, 1 amp going in. plus 5 amps going in must be equal to I1 plus I2 going out. What about for node B? Well, for node B, I1 plus I2 are going in. They're equal to 1 plus 5 going out. Clearly, same equation. So, redundant information. But now that I have that, what I'm going to do is I'm going to substitute and say that I1 must be equal to Vs over 50. Do a little rearranging. I2 must be equal to Vs over 40. And now I can substitute into either one of those equations, and what I will get is that VO over 50 plus, pardon me, I should say Vs over 50 plus Vs over 40 is equal to 6. And in this case, Vs will therefore be equal to 133.33 volts. And here is the voltage across those. Now notice once again, what is my KVL? KVL is trivial. For every loop in this circuit, Vs is equal to Vs. So for KVL, Vs is equal to Vs. That's basically useless information. So I don't even need to worry about KVL because of that parallel definition. Okay? Something else to note here. This was Ohm's law. This was KCL. This is Ohm's law plus KCL. Really, I could have just written this equation right off the bat, couldn't I? Just as I did before with the single loop circuit. Unless the problem required me to calculate I1 and I2, it would have been sufficient for me just to draw the directions of the current arrows and say 1 amp going in plus 5 amps going in is Vs over 50, Ohm's law, plus Vs over 40, Ohm's law. So in fact, I could have just written this equation right off the bat and saved myself a little bit of trouble and made it a little bit easier. So again, learning how to combine Ohm's law with a KVL or a KCL equation will speed things up. It's not that it's required, but as you become more familiar with circuit analysis, you'll get more and more comfortable doing this kind of thing. All right? So, let's go through now and let's do one other thing. Let's look at a couple of quick examples of series and parallel connections. I just want to illustrate that series and parallel is a matter of connectivity, not orientation. So let's look at a few quick examples. For example, what if I've got two resistors connected together like this? Are they in series or are they in parallel? Well, obviously, these hopefully are pretty obvious to everybody. These are in series, right? They're connected together by that single node. What if I draw this? Well, I've basically taken a resistor and bent it around. Now they're next to each other. Are they in parallel? No. Parallel is not a matter of orientation. In this case, there's still a single node that connects the two of them. These are still in series. What about those two? Again, in series. Single node connecting the two together. So this is something you have to watch out for. It doesn't matter how you orient the elements. Look at the connection between them to determine if this is a series connection. All right, what about this? Well, hopefully you look at that and say, yeah, obviously Dr. Holman connected at both ends. Clearly these must be in parallel. What about this? series or parallel? It's drawn kind of a weird way, but look, connected together on this end at this node, connected together on this end at that node. Those two elements are also in parallel. What about this? Looks very much like that, doesn't it? But it's not in series. Look at now what the connections are. Now I've got them connected at this end with this node, and at the other end with this node between the two of them. In fact, those are in parallel as well. These three are in series, these three are in parallel, but they're all drawn very differently. You have to learn to look at the connectivity, not just the way things are oriented in a circuit. Now, before I go, I should mention that sometimes you have circuits that don't really fall into either category. Don't make the mistake of thinking series and parallel is an either-or thing. What about a circuit like this? What if I drew a circuit like this? Are any of those elements in series? Are there any two elements in that circuit that have a connection with no other elements connected to it? Well, this node, no. This node, no, no, no. All these nodes have three elements connected to them. Obviously, none of them are in series. Are any of them in parallel? Are there any two elements that have connections to the same two nodes on either side? Nope. If you look here, you see there are no elements that are connected in parallel to each other. This is a circuit where there are no series or parallel connections. So it is possible to draw a circuit that doesn't have either. So just want to point that out. It's never either or. You can have a circuit that isn't series or parallel. All right? So we've learned a couple of shortcuts based on series and parallel connections. Next time, let's work an example and see if we can apply these and make a brute force problem a little bit easier to solve.